Hello, everyone. I'm Rafal, and I have a pleasure to speak to you today. Let me screen share. Start with my talk, which is titled, Where is my cache? Architectural pattern for caching microservices. But first, a few words about myself. So I'm a tech lead of the cloud native team at Hazelcast. Before Hazelcast, I worked at Google and CERN. I'm also an author of the book Continuous Delivery with Docker and Jenkins. And from time to time, I do conference speaking, trainings, but on a daily basis, I'm a developer, I'm an engineer. A few words about Hazelcast. So Hazelcast is a distributed company, and we are like distributed in two meanings, actually. So the first meaning, we are distributed because we produce distributed software. Our main products are Hazelcast IMDG, which stands for in-memory data grid, which is used for caching or in-memory data store. Second product is Hazelcast Jet, which is a library for stream processing. And our last product is Hazelcast Cloud, which is Hazelcast as a service. But there's also a second meaning to why we are a distributed company. And the second meaning is that we were always a remote company, so we have people all over the world, and we have engineers everywhere, and that's how we operate, and we always operated. Our agenda for this talk is pretty simple. So there will be, I will tell you, there will be a short introduction about caching in general and caching in the context of microservices. And then we will walk through all caching patterns, all caching topologies that you can use in your system. While I'll be talking, I would like you to focus on two things. First thing is, which of this topology do you use in your system? Because most probably you use caching somewhere, and you must use one of these topologies because this list is complete. So you can place yourself somewhere in this list. And the second thing I would like you to think about while I'll be talking is, would it make sense for my system to change to any other topology? So would it be any benefit of migrating to some other topology for my system? And with these questions, I leave you to listen to this talk. So a short introduction about caching. So caching in general, it's everybody uses caching. It's just sometimes we may not even know about it, but we use caching everywhere, and we do it for two reasons. So the first one is super obvious. We do it for performance. So we put cache before because we don't want to do some long-lasting computation. So we already did some business logic, which was time-consuming, and there is now the same. We would need to do the same thing. So we don't want to do the same thing. We already use the cached value, which is super fast. So we do it to decrease the latency and reduce the load. But there is also a second reason why to use caching. And the second reason is maybe a little less obvious, but still valid, and that is the resilience. So we can use caching to improve the resilience of our system. How is possible? So you can think of the following scenario. Imagine you have a microservice architecture, and let's say you're building an Amazon web store, and you would like to have the service for recommendation service. And you have some recommendations for the users. And now imagine that your recommendation service is down. So now instead of returning like, I don't know, not found or something, you can return the cached value, and the user may not even realize, because after all, it's just a recommendation service. So even the point is that even if one service is down, sometimes the cached value is good enough and we can use it instead. That is why caching can also improve the resilience of your system. Now, how it looks like in the microservice world. So that is the classic microservice diagram. That is a classic microservice system. So we have a lot of services. Services have versions. They are written in different programming languages. They use each other. And this is, by the way, this is a very small system. So it's generally, there's a lot of things to think about. Now the question for this talk is, you look at the system and where is the right place to put caching layer? Is it like inside of each service? Or maybe we should put cache as a separate unit in our system, as a cache server. Or maybe we should just put caching in front of each service. And that is what we will cover in this talk. So let's start from the first caching pattern, which is embedded cache. This is the simplest possible way you can do your caching. A diagram. Here's the diagram for this caching pattern. So in our scenario, request goes to the load balancer. Load balancer forwards the traffic to one of the application service. And now inside of each application service, there is like cache embedded as a library. So the request, so application first checks, okay, have I already executed such thing? Can I find it in the cache? If yes, return the cached value. If no, do some business logic, then put the value into the cache and return the response. So that is super simple. That is so simple that not only I was able to explain it in 1 minute, but it's so simple that we could actually think about implementing this on our own. If you happen to use Java, that is how you could implement the simplest caching. So we could have a concurrent hash map, and then there is a request coming to our system. We check if the value is found in the cache. If yes, return the cached value, cached response. If no, do some processing, put the value into the cache, and return the response. So that is probably the simplest way you could implement the cache. But you'd actually better not implement caching on your own. Because implementing caching using a collection, Java collection, or any other language, any collection from any other language is actually not a good solution because it misses a lot of features. So it has no eviction policies, no max size limit, no statistic, no built-in cache loaders, no expiration time, no notification mechanism. So it basically, collection is not a cache. That's the thing. So if we stick to Java, there is a lot of libraries that you could use for caching. One of the very good caching library you can find in Guava, where you can define all these lacking features that were lacking in the Java collection upfront in the constructor, in the builder, and another good solution is, by the way, EHCache. Now, if we think about caching, we can use a library like Guava, EHCache, but we could even move this caching to the one layer higher, one abstraction layer higher, and then put the caching into the application framework. So if you are like most of the people nowadays and use Spring for your application framework, then to enable caching, all you have to do is to add the cacheable annotation to your method. And now every call to this method getBook named by ISBN will first check if the given ISBN is found in the cache. If yes, return the value from the cache called books. Only if the given ISBN is not found in the cache, we execute a method, the method findBook in slow source. So in Spring, caching is done even simpler, but be careful because for some reason Spring by default they use concurrent hash map, so you are better off by changing your cache manager in your Spring configuration. So all good so far. We have like the simplest caching possible, embedded cache. All works fine. But there is one problem with this scenario. Imagine that request goes to load balancer and it's forwarded to the application at the top. We execute the business logic, we put value into the cache, all good. But now the same request can go to our system, go to the load balancer, but now it's forwarded to the application at the bottom. And now what happens? We need to do the long-lasting computation once again, because these two caches, they are completely separate. They don't know about each other. So each application has its own cache. And that is something we can improve with embedded distributed cache. So embedded distributed cache, it's still the same idea. I mean, so it's not a separate pattern, but this time, like all the caching libraries, they will form one caching cluster, and so they will use the same storage for caching, basically. So this time, instead of the Guava, cache, or Java collection, we will use Hazelcast, which is a distributed, which can be used as the distributed cache. So look what happens. So now a request goes to load balancer, it's forwarded to one of the application replicas, and now applications, they have embedded cache, like a library for caching, but this time, all caches in every application replica, they form one consistent caching cluster. So no matter which application replica we use, they will use the same storage for caching. How it looks like in the code. So if we would like to code it, if we stick to this example with Spring, all we need to do is to change the cache manager and tell Spring, hey, Spring, use Hazelcast for caching, and that's it. So a short demo how it looks like in practice. So in my in the IntelliJ, you can see so it's just the simplest Spring Boot application you can imagine. There's controller, there is service, there is our cache configuration, which is exactly what we've seen on the slide, and there is our service with a method which is cached, and to simulate the long processing, we just put sleep. So if I start this application, we can see in the logs that it's starting. It's Spring and Java. It will take some time, but in a second we should see that the caching cluster started. That is what we will focus on. That is the log, which in Hazelcast means, okay, I started a caching cluster with one member. Let's start the second instance of the application and see what happens. So we start a second instance of the same application, and when it started, we should see that they both created one consistent caching cluster. So no matter which application replica we use, we will use the same cache data. So one second more, and this log means, okay, we formed a caching cluster. So and we look at another log, so it's also it formed one consistent caching cluster. Now you can see that here is my cache configuration. So there is nothing special here. So first question, I will step this application. So first question you may have, how it's possible that these two application replicas, they found themselves? Obviously, I've run it just now on my laptop, so by default they used multicast, so it was easy. But multicast is not good for production environment usually. So how can the instances find themselves? So we thought about this problem, and we came up with the idea of discovery plugins, which are, by the way, automatically detected. So you run Hazelcast on AWS, and what happens? Hazelcast detects, okay, I'm running on AWS. I should use AWS plugin. So I use AWS plugin, and then use AWS API to discover other members. So that is a really nice way that you don't even have to think too much about it. Hazelcast will find the other instance. And the same with Kubernetes, with Azure, GCP, we have plugins. If you're running like on premises environment, which we don't have a plugin for, you can either write your own plugin, like community plugin, or piggyback on Eureka or Zookeeper, so some service registry. Okay, so if you, by the way, if you are interested how to configure this, I will share the resources, but you can also find a lot of our documentation and blog posts. We publish a lot of this, how to configure this properly. Okay, so we have our we've ended up with this embedded distributed cache. So let's do a short summary of the embedded caching. So if you use embedded caching, what it means for you, why would you use it, and why would you not use it? So the advantages of using embedded cache is that configuration is super simple because your cache goes together with your application. So you don't have any extra deployment. You don't need like ops team or DevOps effort for the cache to set up the caching. Another pros is that you have very low latency data access because your cache is inside your application. So there is nothing better we can do. And from the downsides, like the management is not so flexible because if you'd like to scale up your caching cluster, you need to do it together with your application. And it's limited to JVM-based application. To basically your cache solution is limited to your language in which your microservice is written because you embed it. And also from the downside, data is co-located with the application, which may be may not be a problem. Okay, we covered embedded caching. So the next pattern you can use, next topology you can use is a client server. So client server is kind of database style. So when you deploy your server separately and then use clients to connect to the server. How it looks like. So this is like a diagram for the client server architecture. Request goes to the load balancer again. It's forwarded to one of the application replicas. And now application uses cache client to connect to the cache server, which is deployed separately. If we compare this diagram to the embedded caching, there are two differences. First difference is we have a new entity on our diagram. We have something new. We have cache server, which we need to maintain separately. So good thing is that we can scale it up, scale it down separately. But another thing is that we need to think about its management and to think about security, etc. Usually, I can already tell you that in big enterprises, what we see from our customers is that this cache server is usually maintained by a separate team, ops team, or even a separate department. So that is how it usually works. But there's also a second difference. If we compare this diagram to the embedded diagram, there is also a second difference. And this is this part. So now the application uses cache client to connect to cache server. And cache client does not need to be written in the same programming language because there is a well-defined protocol between client and the server. So we can write a cache client in any language, which means that you can write your application service in any programming language you want. And that is a very common scenario that we have our microservices written in different programming languages and they connect to the cache cluster, which is deployed separately. And that is such a common thing to do that if you use some other solutions like Redis, Memcache, that is the only topology that you can use actually, because Redis is written, I guess, in C and Memcache, I think the same. So so we can only use, so we cannot embed it in your microservice. So the only way you can use it is client server. How to configure this? So in case of Hazelcast, you can use start at sh if you go on premises, but if you use Kubernetes, for example, we provide Helm chart and operator. So for example, to start a Hazelcast cluster on Kubernetes, you can use Helm install. How does the client looks like? So that is the simplest client configuration. Yeah, you remember the story with the discovery plugins. So if you run this in Kubernetes, for example, Hazelcast will discover, okay, I'm running Kubernetes. I should use Kubernetes plugin, and I should query Kubernetes API to find the cache server, and it will all work smoothly. So we ended up with a diagram like this, like our client server diagram. So we have, and as I told you, like this cache server part is usually deployed, maintained by a separate team. That's what we see, and it could be in big enterprises usually even a separate department. So we could even go one step further and move this server part into the cloud. So cloud is it's kind of client server, but it's a very specific client server where your server part is not maintained inside your organization. So it looks like that it's still like the same as client server, but to connect to the server, we connect to the cluster, to the caching cluster, which is deployed in the cloud. And we don't have to think about all these management things because they are provided as a service. But obviously we need to pay for this, which is actually everything is moving to the cloud, so it's usually cheaper to pay for the SaaS solution than to maintain it on your own in your own infrastructure. So how it looks like if you would like to configure this. So in case of Hazelcast Cloud, here is your client configuration. So you need to specify. So you set up your. I'll show you in a second. But you need to set up your caching cluster in the cloud, and then using Web Console or CLI, and then get the discovery token, put it into your configuration, and that's it. So let me show you a quick demo of how it looks like in practice. So I have here, if you go to the cloud hazelcast.com, you don't even need to register. You can just click login with Google or GitHub. Then you got free credit. So you can, I really actually encourage you to play with this. Then you can create a new cluster like Rafal tests, DevDays, and you can choose the underlying cloud provider, select the region where your cluster should be running, select the cluster size, select Hazelcast version if the persistence should be enabled, and you have some other features, and then create cluster. And now the cluster is being created. When it's created, we will get the discovery token, put it into our client configuration, and start the application. Now, one important thing that you have to think about is, you remember I've selected the underlying cloud provider. So this underlying cloud provider should be the same where your application is running, because we don't want to connect from the application running on AWS to the cache which is running on GCP, because that would be slow. Another thing you have to think about, you should use the same region, because we don't want to connect to another region. And there's one more thing you have to think about, is like to run in the same VPC. We provide a way to do a VPC peering between your client and the server. So then they are really running in the same like virtual network, and the latency is good. Our cluster is running. We can check the discovery token, copy this into our client application, and I will show you. Let's close this and that. I will show you the configuration. So cache configuration. So this is our discovery token, and I call my cluster Rafal test DevDays, and with this we can start the application, and it should connect to to our cache cluster in the cloud. Obviously, now I'm not doing this right because I'm connecting from my laptop to the cluster in the cloud, but you get the idea. You should actually think about this because otherwise your latency will suffer. So it's connected to the 3 members which are running in the cloud. These are actually public IPs from AWS. So everything works as expected. I really encourage you to play. I will share with you this source code, where you have all the patterns implemented, so you can play with this. And I really also recommend playing with cloud Hazelcast, where we can play. You can use it for free, actually, with some free credits, and play with this, because then you will get a better idea what it means. A short summary of the client server and the cloud caching. So the good things about the client server is that data is separated from the application. Also, the cluster, you can manage this separately, so you can scale up your caching cluster as you want. And it's programming language agnostic because we use cache client to connect to the cache server. From the downsides, we have separate ops effort to maintain, to deploy and maintain the caching cluster, or we need to pay for the cloud provider. And you need to, I mentioned here high latency, but it's not necessarily higher, but you have to think about latency. So you have to think about 3 things. First, select the same underlying cloud provider, select the same region, and do a VPC peering. And then the latency is good. If you go on premises, then you'd better deploy your caching cluster in the same local network. Because something to keep in mind is that this caching is a domain of low latency. It's low latency domain, so we need to really think about it. Okay, we covered like the client server, cloud. So the next caching pattern we will use is Sidecar. So Sidecar is because so far it's like embedded cache, client server. It's nothing so much new, but Sidecar is something, some kind of a new pattern, because it was the idea of Sidecar is together with containerization and with the Kubernetes, Azure containers, etc. How it looks like. So this diagram is Kubernetes specific. Sidecar is not only for Kubernetes, but it's mainly now seen in Kubernetes. That's why I made this diagram Kubernetes specific. So a short introduction, if you haven't heard about Kubernetes or sidecars, a short introduction about Kubernetes. So in Kubernetes, a deployment unit is called a pod, and a pod can contain one or many containers. Usually, we'll see that a pod has just one container, and it's your application container. But sometimes a pod can have additional containers for some additional functionality. For example, this additional container can be a container which will redirect, which can be an agent that will redirect your application logs somewhere else. So it's some kind of, it adds some functionality. And this additional container is called a sidecar container. And something that Kubernetes guarantees is that all containers in one pod are deployed in the same physical machine. So this is, you can take it for granted. So with this in mind, we can see how our cache as a sidecar looks like. So there is a request going to our system, goes to the Kubernetes service, which is a load balancer. It forwards the traffic to one of the Kubernetes pod, and inside the Kubernetes pod is the application container that receives the request. Now the application container uses cache client to connect to the cache server, and this cache server is deployed as a sidecar container inside the same Kubernetes pod. So this Cache container is a cache server which is always available at the local host, because the application is sure that your cache container is deployed in the same physical machine, and it can use local host to connect to this cache container. And all the cache containers, they use the same, they form one caching cluster. So this solution is, if you think about it, sidecar caching, it's somehow similar to the embedded cache, somehow similar to the client server. It's similar to the embedded cache because we use the same physical machine for caching and for cache server and the cache client. It scales up and down together with the application because we scale the pod. And there's no discovery needed because it's always available at the local host, so the same as embedded. However, it's also similar to client server because we can use different programming languages for the application and for the cache, because after all, we use a cache client to connect to the cache server. So it's somewhere in between. How it looks like, if you'd like to configure your cache as a sidecar, how it looks like. So this is how your cache client, your application looks like. If we stick to this to the Spring example, you need to specify in your client configuration, my cache is available at the local host. That's it, because you just know. So it looks like a very static configuration, but it's actually good for even like production systems. How your Kubernetes configuration can look like. So you need to have in your deployment, you need in your pod, you need to have two containers. One is our application, so this is custom, like this is your business logic. And the second one is a cache server, which is always the same. So you see, it's very simple. So one of the, so a short summary about Sidecar. So the configuration is very simple. It's programming language agnostic. We have low latency, and there is some kind of isolation of data in the application. From the downsides, it's limited to container-based environments. As I told you, you will see it mostly in Kubernetes, but it's not only for Kubernetes actually. The management is not flexible again, because like if you would like to scale up, scale down, you need to do it together with your application. And data is collocated in the same application, collocated with application in the same pod. So data isolation at the pod level, which may be good enough or may not be good enough for you. Okay, we covered Sidecar, and the last caching pattern that you can use, the last caching topology, is Reverse Proxy. Reverse Proxy is something completely different. It's completely different than what we've seen so far. Because so far, your application was always aware that such thing as a cache exists. Now we will make the application unaware of the caching. So we will put caching in front of the application. So application will not even be aware that such thing as a cache exists. How it looks like in a diagram. So request goes to our system, it goes to the load balancer, and now just before the load balancer or after the load balancer or together with the load balancer, there is a cache. And now if the given request is found in the cache, the response is taken from the cache and returned to the user. And it does not even touch the application. So that is the whole thing. Only if the value is not found in the cache, it goes to the application service. A very good solution for such scenario is Nginx, because Nginx provides caching functionality, and it's a very mature solution. So I can recommend using Nginx for reverse proxy caching. If you would like to configure Nginx, this is the simplest configuration you can use in your Nginx configuration to enable caching. Nginx is good because it's mature, but it misses some features. So it's only for HTTP, maybe it's not such a big deal, but it's not distributed, is not highly available, and it can, it actually doesn't store data on the disk. It stores data in memory, but it can offload your data to disk, which, for example, which can affect the latency, which can affect the data access. For example, if you use Hazelcast, you are guaranteed that your data is stored in memory, so you can reason about the latency. In the case of Nginx, data can be offloaded to the disk. But still, Nginx is a way to go for the reverse proxy caching. Now, the last variant, the last variation of the reverse proxy, and the last variation of caching topology for this talk is to connect reverse proxy with the sidecar and to create like reverse proxy sidecar topology. How it looks like. So this is our diagram. Again, we will limit ourselves to the Kubernetes. How it looks like. So request goes to our system. It goes to Kubernetes service, which load balances the traffic to the Kubernetes pods. Request goes to the one of the Kubernetes pod, but now it's not the application container that receives the request, but that is something what I call reverse proxy cache container, which is basically cache server, but also the network interceptor, which checks if the value is, if we have this request in the cache, if yes, return the response, if no, go to the application container. But again, if the request is found in the cache, we don't even touch the application container. So if you think about like, if you think about this idea of reverse proxy caching and reverse proxy sidecar caching, so it actually has some good things and bad things. And maybe let's start from analyzing this from the good. What is the reason why you would use it? So what is good about reverse proxy caching? You remember this microservice architecture we've seen at the beginning of this talk. So a lot of services, they have different versions, they are written in different programming languages, they use each other and generate a mess. Now, you can measure some performance, you can look at the diagram like this and say, I would like to introduce caching in a service 2 version 1 and service 1. And you can do it in a declarative manner at the configuration layer. So you don't even touch the code of the service. And that is actually the whole beauty of reverse proxy caching. Then you, at the configuration level, you can introduce caching. So you can improve the performance of your system at the configuration level. How it looks like we stick to the Kubernetes, how your reverse proxy sidecar caching configuration could look like. So this time we will need three containers, maybe now starting from 2 containers, 1 init container, starting from the bottom. So at the bottom we have our application, that's the easy part. Next one, we have our caching proxy, which is container which is cache server plus network interceptor. And we also need an init container with a script which will change the IP tables so that a request from outside to the to our pod will not go to the application, but it will go to this caching proxy. So we need to tweak the IP tables. Okay, about this reverse proxy sidecar. So this diagram may make you think about and this whole idea of having like a separate caching proxy. It may make you think about like Istio and service meshes, because actually that's the same idea, that we introduce some functionality in a declarative manner at the configuration level. And Istio, actually the Envoy proxy used by Istio recently implemented the caching functionality. So I think soon you will see this idea of reverse proxy sidecar caching inside service meshes. It's still not like mainstream, but you will see it soon, I think. But okay, I also mentioned that there is no such thing as a free lunch. So there are some drawbacks of using reverse proxy and reverse proxy sidecar caching. And actually, if you look anywhere on the internet and ask the question, what is the most difficult part of the caching? Everyone will tell you the same, that the hardest part of caching is cache invalidation, meaning when to decide that the data is in the cache is already stale. I should not use the cache data. I should use the real. I should go to the database. I should go to the real service where the single point of truth. And that is difficult because if the application is aware of the caching, we can use some business logic to decide, okay, I would like to evict this cached value or not use the cached value. But if the application is not even aware of the caching, then we are stuck with the standard HTTP things like timeouts, e-tags, basically timeouts. So that is like the thing that becomes more difficult with the reverse proxy caching. Okay, a short summary. So about reverse proxy caching, like good sides, and why you will use it is that there is no change to the application to introduce the caching. So it's programming language agnostic, everything agnostic. You define your caching in a declarative manner in your configuration. And it is very consistent with the containers and the microservice world. So I strongly believe that will be the future of caching as soon as there will be some major solution for the reverse proxy sidecar caching and inside service meshes. And for the downsides, like we mentioned, the cache invalidation, there's no major solution for reverse proxy sidecar. For just reverse proxy, you can use Nginx, and it's protocol based. Okay, we covered like all caching topologies or caching patterns. So as a short summary, I'll try not to repeat anything I've already said, because that could be boring. So what I suggest as a summary is a short, very simple, maybe oversimplified, but something that will help you decide which caching solution is for you. So I suggest a decision tree. So the first question you can ask while deciding on the caching topology is, does my application need to be aware of the caching? If no, do I use containers? No, you can use reverse proxy. If yes, you can use reverse proxy sidecar container, probably inside service meshes as soon as it becomes something major. Now, if your application needs to be aware of the caching, then the next question is, do I have a lot of data or some security restrictions? If no, should my application be language agnostic, or do I use containers? If no, use embedded or embedded distributed. If yes, you can use Sidecar. Now, if you have a lot of data, you have some security restriction, you basically work in a big enterprise, then the last question you need to ask is my deployment cloud? If yes, go for a cloud solution. If no, use client server on premises. And as a last slide for this presentation, I put here some resources. So the first link are all these code samples and even more what I presented as a demo. So I recommend you playing with this because this will give you a better idea of what we are talking about. Second link is a blog post about configuring Hazelcast as a sidecar for the sidecar caching. Third one is our prototype for Hazelcast as a reverse proxy sidecar container. And the last one is a very good video talk about Nginx as a reverse proxy caching. So with this last slide, I would like to thank you for listening. It was a pleasure to speak here, and I wish you a great day and the rest of the conference. Now let me stop screen sharing and see if there are any questions. So I don't see any questions, which means that I just can tell you only thank you again for listening. See you.